Today I wanted to talk a little bit about geology and their connection to pots and rocks and things that we use. So I'm going to divide the talk into three parts. We're going to talk about the history of the Earth, a little bit just kind of in general terms, the origin of the materials that we use for pottery, how they originate by geological processes, and then lastly, if we have enough time, I want to talk a little bit about the local geology here, what happened here geologically in the past, because this is a really fascinating area for geology. A lot happened here.
Welcome to the Potter's Roundtable, a monthly podcast where we share our passion for the ceramic arts and a collection of topics specific to potters. Remember to subscribe so you don't miss a single episode. Enjoy the show.
Today I wanted to talk a little bit about geology and their connection to pots and rocks and things that we use. So I'm going to divide the talk into three parts. We're going to talk about the history of the Earth, a little bit just kind of in general terms, the origin of the materials that we use for pottery, how they originate by geological processes, and then lastly, if we have enough time, I want to talk a little bit about the local geology here, what happened here geologically in the past, because this is a really fascinating area for geology. A lot happened here in the past. This is much, to me, much more interesting than living in Ohio, or western Illinois even.
Or Connecticut.
Yeah. Some really interesting stuff happened here that we'll talk about. So talk about the Earth first, and because the Earth is about 5 billion years old, and I'm going to try to condense it to about 15 minutes, so I'm going to have to leave a few things out. So, just starting at the beginning, right now the best estimate is the Earth formed about 4.6 billion years ago. You know, this is one of the hard things about being a human being, is because we live in such a tiny little slice of the universe in terms of time, extensive time, in terms of distances, in terms of light waves and things. They're so much smaller than we are and bigger than we are that it's really hard to even imagine. But they figure the Earth is about 4.6 billion years old, and that it originated from dust and other fragments of other planets and stars and things that were circulating around, attracted by the sun, and they basically were swirling around the sun, and after a while gravity pulled them together, and they collected and formed this early ball of stuff. And about 4.5 billion years ago, after all this celestial stuff had collected, it started to separate into layers. The heavier materials, like asteroids that were mostly metal, would start to sink toward the center because this chunk of debris had enough gravity of its own now that it could pull on things. So the heavier materials, like the meteorite fragments that were mostly iron, would be pulled more toward the center. So the surface, the Earth started to segregate into sort of three different layers or three different zones. And one was the surface crust on the outside, which was mostly the lightest weight minerals and the lightest weight materials. And then there's another layer underneath it called the mantle, which is kind of intermediate weight stuff. And then there was the core. And so what the core ended up being is mostly iron and nickel, is from the meteorites, and it's basically where most of the weight of the Earth, frankly, is in the core. The first life, the best estimates now from studying fossils is that the first life they figure probably appeared on Earth. This would be single cell life, about 3.8 to 3.4 billion years ago. So not that long. This has been a fairly recent change. We'll talk about it later, but they used to believe that life only began about 500 million years ago. But they're finding evidence now, and with new analytical techniques, that they think life started a lot sooner than they originally thought, and that it, in fact, started not that long after the Earth was formed. Originally, the surface of the Earth, after all these things impacted the Earth, the surface of the Earth was basically molten. And then it cooled down, and during that molten stage, the Earth was settling and segregating into these different shells or these different regions. But not long after it cooled down, they're finding evidence of first life. Geologists, when they talk about the age of the Earth, they tend to divide it. They divide it into time periods, and the time periods are based based on what was happening in the rocks. Before they even understood a lot of what was going on, if they'd see a change in the rocks, like something happened, like maybe a new life form appeared or some other life form, some fossil disappeared, they use that as a demarcation or a change between different periods. So I'm not going to go into all the details. But the biggest sort of divisions of geologic time are these. The Cenozoic, which we're still living in. Cenozoic means recent life. This is where they were basing it on when they saw evidence of life in the rock. So Cenozoic era started about 66 million years ago. And then before that, the Mesozoic, which means middle life, started about 252 million years ago, give or take a few million years. And the Paleozoic, which means ancient, started about 542 million years ago. And then according to the original classification, these all have subdivisions underneath these main categories, and then subdivisions under the subdivisions, which we don't have to go into here. But the earliest subdivision of this Paleozoic was called the Cambrian period. And so everything earlier than that was called the Precambrian. There are a lot more subdivisions down here, but this started 4.5 billion years ago. Basically, that's what I mentioned, the same time as the Earth was starting to segregate into these recognizable layers, the crust, the mantle, and the core. And so there are a lot of different, and a lot of these early terms, for instance, I just mentioned the Cambrian, that was named after a tribe in Wales, the Cambria. Well, the Cambrians, I forget what the original, but so a lot of the early work that was done in Europe and Britain was named after the Ordovician. There's another period in here called the Ordovician period. That was named after another Welsh tribe, the Ordovices. And so a lot of the names of the smaller divisions came from either the location or something that was happening in that area when they first started examining the rock. So we'll just use this as a framework that we can refer back to. Okay?
MYA?
Pardon?
MYA.
Million years ago.
Oh, million years. But you said that the Precambrian is 4.5 billion.
The Precambrian basically started, they can date it now back to with rock, because there are still, believe it, the thing that's amazing is there are still rocks around. They're not very common, but there's still rocks around from that you can recognize as being that old. They have dating techniques now where they can date the rock. And in Greenland is one in particular where there's some Greenland and Australia, parts of Canada, there's some incredibly ancient rocks that go all the way back to basically when they think the Earth formed. I mean, incredibly ancient ones that they've been able to identify. But the big thing to talk about in terms of bringing it more up to date is, so basically the Earth is this huge ball of rock and iron in the center. But the big thing is it's not static. There are a lot of processes and motion and things and activities going on there. So we think about we're just living on a big ball of rock, but it's not at all dead. There's a lot of a huge amount of activity going on the surface and underneath the surface. The core of the Earth actually consists of two parts: a solid inner core and a molten outer core, basically molten iron and nickel. And currents, movements, or movement of the liquid in that outer core is what generates the magnetic field of the Earth. That's what actually generates our magnetic field, is this movement of the liquid, the molten iron in the outer core. And the next layer above that, in the mantle, there's such tremendous pressure and heat at these depths in the Earth that the rocks and the material down there is actually slowly flowing. You can think of it as sort of almost like toothpaste consistency. I mean, we think of the rocks as being hard and brittle, but when you put them under enough pressure and under enough heat, they actually become soft and plastic. Kind of like, you've all heard the term, we call it pyroplastic, that when you fire clay, it gets slightly soft and moves. Well, that's what's happening only with the addition of pressure. That's what's happening to the rocks all the time deep in the Earth, in the mantle. So the rocks in this intermediate zone in the Earth, which is a big wide zone, are actually moving, and we'll talk about this later, but they actually are moving around in currents. They're flowing, actually, constantly underneath. So, and then in the crust itself, there's a huge amount going on. But by the way, if you think about scale, if the Earth is about the size of an apple, the crust is like the skin of the apple. And we're only living on the barest surface. The crust is roughly 30 to 35 miles thick. Okay? Well, the Earth is 8,000 miles in diameter. So we're only living in like the whole crust, the whole part that we think of as, where all our mines go and everything else, is only 35 miles deep, and we're only living on the surface of that. So it's tiny relative to the mass of the rest of the Earth. But there's a lot of activity in the crust, and the driving force that they've realized now for all the geological processes that we think about, and you've probably heard of this, is Continental Drift, or they call it plate tectonics. They realized in the 1960s that the whole surface of the Earth, the crust, if you look at it, is divided up into like pieces, like a jigsaw puzzle. And these are called plates. And they're probably on the order of 20 some odd plates, pieces of the Earth. And these plates are moving, they're shifting around. And floating on top of each one of these pieces of Earth is a continent. So the continent isn't itself the whole plate. There'll be a portion of the Earth, like a piece of the puzzle, and there might be on top of that a piece of what we would call a continent. And these pieces are actually shifting around over the surface of the Earth. We'll talk about how and why, but they're moving around. And so all the things that we think about in terms of, when we think about geological activity, volcanoes, earthquakes, those are all caused by the shifting around of these plates on the surface of the Earth. So it's not just the continents. The old term is continental drift because they can see these continents. They have evidence of the continents moving. But it's not just the continent, it's the whole plate that's supporting the continent. So it's like a boat, and the continent is a passenger on the boat. And these things are shifting around constantly over the surface of the Earth. And what's moving them is the currents in the mantle underneath. There are convection currents. There are natural currents. Hot material rock is rising underneath, and colder material is sinking back toward the center of the Earth. And as these huge currents in the underlying rocks move, they drag the plates with them. So in some cases, you have plates that are moving apart. If a current wells up toward the surface of the Earth and spreads as it reaches the surface, then it tends to push the plates apart. In other cases where the current is dropping down in, it tends to drag the plates together. So the plates are constantly jostling around. Some of them are moving apart, some are separated. For example, right now, the Atlantic Ocean is getting wider. The plate that Europe and Africa, the plates that Europe and Africa are on, and America are on a different plate, they're actually spreading. So the Atlantic Ocean is widening by about 1.5 inches every year. They say at about the rate your fingernails grow. And whereas the Pacific Ocean is closing, in millions of years or whatever, there may not be a Pacific Ocean at all. We'll talk about this when we talk about the local history. But whole oceans have come and gone over the history of the Earth, and continents have collided and combined and split in new ways and created new continents. And this has happened a lot of times over the course of the history of the Earth. But all the things that we think about when you hear about earthquakes and volcanoes, that's all happened because of these continents colliding or pulling apart. So there's a lot happening on the surface of the Earth. We tend to think about it in terms of these sort of instantaneous things like earthquakes and volcanoes. But all the time, there's this motion going on. These things are happening. And only when it finally reaches a critical point do you have like an earthquake or you have a volcanic eruption. And in addition to that, in addition to the other point is that, and along with this, is the Earth is, and I mentioned this in the little blurb for the advertisement, the Earth is constantly recycling its own materials. So that you have some of the portions of the surface of the crust that are pulled back down into the Earth and remelted and then come back up again to the surface of the Earth. So that it's remelting its own materials inside the Earth. And also you have the weathering and erosion. So when you have things like mountains and land masses, they're being worn down by wind and water and ice and erosion of other materials. And that stuff ends up in the sea. And then that stuff gets pulled down into the center of the Earth and remelted and reworked and may come up as a volcano somewhere else. So the Earth is constantly, very slowly, but it's constantly recycling everything. So from that point of view, it's really unusual that we can find evidence of any of these really old continents or old rocks at all, because most of it, in fact, is gone. Most of it has been recycled maybe multiple times. So it's actually very surprising when we can find an area of the world that has remained intact, where basically nothing has touched it since it's originally formed. So in terms of geological processes, in terms of what's going on, well, I mentioned there's this what's called plate tectonics. That's the name for where you have the plates colliding and spreading. And then you have mountain building. People used to wonder, when I first started studying geology, I have 2 degrees in geology. That was originally what I went to school for. When they were originally studying about mountains, they understood the mountains and the structures, but they didn't know where did the force come to make the mountains, what actually made the land pile up and form mountains. And then they realized it was the collision of the plates. That's what finally did it. For instance, the mountains in India, the Himalayas. India used to be a separate continent, and it slammed into Asia and created the Himalayas. The Andes Mountains running down the whole western side of South America are there because the Pacific plate, the bottom of the ocean, is slamming into the west coast of South America. So if you notice, you don't form mountains or you very rarely form a mountain in the middle of a continent. They're all formed on the edges of continents where one continent is plowing into another one and literally crumpling and bending and piling up the rocks. Very slowly. You can't stand there and watch the mountains kind of get pushed up, but it's happening over, relentlessly over millions of years. And so because I remember that was kind of a big discovery when I was early on in geology, was they understood all about the structure of mountains and the rocks and everything, but they just didn't know, what caused them to actually form. And plate tectonics, the movement that was the answer. It solved a lot of these things that they understood, except for the fact was, why did it happen? And all of a sudden, understanding about the fact that you had these movements of these huge pieces of the puzzle on the surface of the earth, it answered all the questions. It said, that's the answer. That's why it happens.
We hope you're enjoying the show. Please take a moment to leave a 5-star review on your podcast platform of choice. It really helps new listeners find the show. Don't forget to subscribe to receive updates as new episodes are released. And if you'd like to support the video and podcast production of the Potter's Roundtable, become a patron. Go to patreon.com and search for the Potter's Roundtable. Your support will help us achieve our goal of creating a digital library spanning the ceramic arts for use by educators and artists alike. Thank you for your support. Now let's get back to the show.
So in terms of major processes, you have volcanism, you have volcanoes basically, where you have molten material coming up to the surface of the earth and erupting. Or in some cases, it doesn't actually make it all up to the surface of the earth. It may rise up into the crust and then freeze and solidify there and stay there. And maybe it's exposed millions of years later by erosion, but it doesn't actually erupt on the surface. There's a second process called metamorphism, and that's where previously existing rocks are changed into something new. This usually happens at great depth in the earth. If a rock gets pushed way down in the crust, miles down in the crust, there's tremendous heat and pressure down there. That's enough to actually chemically and physically change the structure of the rock into something different, and we'll talk about that. So that's part of the recycling process. And then there's sedimentation, which is where, when rocks are on the surface of the earth, where rocks are eroded and weathered and changed by ice and wind and water and abrasion by other rocks, the debris, the fine particles, the sand and the dust, basically is carried by water or wind and settles somewhere and builds up as a deposit. And then actually eventually, if you build up enough of it, just the weight of those materials compresses it and hardens it and turns it into rock. So as a result of this, there are 3 main categories of rocks. If we start looking at rocks now, there are what are called igneous rocks, and these are rocks that essentially form by heat or fire. That's I-G-N-E-O-S, igneous. Igneous rocks. These are formed by heat or fire. And as I mentioned, there are 2 paths that this can take. In some cases, this means like if I have a volcanic eruption of molten rock at the surface of the earth is called lava. And so if I have an eruption of lava on the surface of the earth, when that lava cools, it can solidify and form what we call a volcanic rock. And there are all different kinds of volcanic rocks. I'm going to pass around some examples. Here you already passed around one piece already, but I'll pass around a bigger one here. This is a piece of obsidian, like this piece that Sally passed around was. This is basically volcanic glass, and the thing is, this is not much different than our glazes. Our glazes are glass. Well, this is naturally occurring glass, basically. This is the same way, we talk about our glazes. We don't want them to crystallize. We want them to stay glass. Well, this is naturally occurring glass. The composition of this is not that much different from our glazes. So I'll pass this around. So this is not crystalline. This is just glass. Now, on the other hand, I may have a composition that crystallizes and forms little grains of minerals. This is a sample that I collected in Hawaii. This is called basalt. But this is a different kind of. So this is not glass. This is crystalline materials. There are several different minerals in here. But this crystallized a little more. This cooled a little more slowly than that. That cooled really fast, so that no crystals formed. This cooled a little more slowly, so you can't see the individual crystals in it. It's still cooled pretty fast. but it cools, and if you turn it over on the other side, you'll see some little green specks where one mineral, olivine, started to crystallize out of it. But it still cooled pretty quickly, and all the holes are gas bubbles. So this was lava that erupted on the surface of the Earth, and it had a lot of trapped gas in it, and before the gas could escape, the rock solidified. Whereas that had very little gas trapped in it, which is why you don't see the bubbles in it. So if you can imagine, rocks coming up to the surface and erupting, there are all kinds of possibilities for different compositions and different characteristics of lava. The Hawaiians even have names for, it's typical of a lot of cultures, where they have a lot of detail of the environment. The Hawaiians have names for two different kinds of lava. One's called A'a, and the other's called Pahoihoi. And what they recognize is that one of them, Pahoihoi, flows and moves very quickly, and it's very dangerous. You have to get out of the way, where A'a is very slow moving, and you can stand there and watch it move. And that's because when one of the kinds of lava melts, it's really runny, kind of like our glazes. And when the other one melts, it's thick and stiff, and so when it flows, it doesn't move very quickly. You can literally stand there and watch it come toward you, and you back up a little, and you back up a little bit. And so early on, they realized the distinction that you've got to be careful when Pahoihoi is erupting, but not so much when A'a is erupting. And the same volcano, as it was dissolving and melting different rocks under the surface of the Earth, it would change composition. So one time it might put out one kind of lava, and another time it might put out another kind of lava. And different volcanoes put out different kinds of lavas. So and then now, if the rock doesn't make it all the way up to the surface of the Earth, and so you have this molten rock underneath the Earth, it's called magma, M-A-G-M-A. And this is molten rock, and it might just come up and sort of rise up into the crust, and then it cools and slows down and stops, and it basically solidifies. And it might take literally millions of years to cool down. Well, when it does, usually they have a chance to form crystals. When it cools so slowly, just the same way, you probably, again, this relates to our glazes, but an important part of firing a glaze is not how you fire it, but how you cool it. And a lot of glazes, if you slow down the cooling or you add a hold at the end of the firing, you can encourage crystal growth, which you wouldn't normally see if you let it cool down quickly. This is especially true in electric kilns. So if you ever want to try something interesting, if you're firing an electric kiln like Cone 6, extend the firing, put a hold on it, or slow down the cooling a lot. You may get something that looks like a completely different glaze because you encourage crystal development. The crystals can only form slowly. And so as the atoms basically are moving around and collecting together and grouping in bunches to form these little crystals. So the atoms have to have time to move. And if you allow them to do that, you form the crystals, you can get a glaze that looks very different than if you cool the same glaze down quickly. So underneath the Earth, where it literally can take millions of years for the rock to cool, you typically get rocks that have very obvious crystals, and the best example is granite. And a lot of these rocks that you see that they sell for kitchen counters and bathroom counters, and they have this coarse structure, that's because they were formed deep in the Earth, and they had time to separate into all these different crystals. So this has 3 different materials in it. It has sort of medium gray quartz, and it has the white, large areas of feldspar, and the black is mica. And so this cooled so slowly that all the elements were there. And all these same elements, by the way, are in the obsidian. If that cooled slowly, that would form this. It's almost the same composition, the same total composition. But in that case, it cooled so quickly, nothing could happen. In this case, that almost the same kind of lava cooled so slowly that it actually separate into the separate minerals. That's granite. And there are lots of other related rocks that have similar compositions with different names. So that's a common example. Okay. So those are igneous rocks. Now, yes, sedimentary rocks, and this is where other rocks are worn down by erosion, by weathering, and they're basically torn to bits. They're ripped apart. In some cases, they might change chemically a little bit, or they might get broken down. You hear stories about, for instance, how the air pollution is etching and changing statues and the facades of buildings and things because it's eating them. So the same process is happening on rock. Frost is a really big action. If a little crack, you have a rock and water gets between it, the water can actually split the rocks. So you can't, especially in parts of the country where you have freezing and thawing, you get much more rapid weathering than in areas where you just have constant, no temperature changes. Because you're freezing and thawing and expanding and contracting. And basically the rocks get broken into smaller and smaller parts. And then these parts can be carried by streams or blown away by wind or carried into rivers. And eventually they all end up in the ocean or somewhere. They end up deposited somewhere. And if those rocks, if let's say you have a river that dumps into the ocean, and it carries all this sediment and the particles with it, and it dumps there, over millions of years, you can get incredibly thick deposits, miles thick. And at the bottom of that pile, the pressure is so great that the rock actually gets compressed, the loose stuff actually gets compressed into a rock. And I've got some examples of that. This is Dolomite. This is a sedimentary rock. And this is right here from 2 miles down the road. This is actually a very valuable rock. This was used by the steel industry as the flux to melt steel. And the stuff from Bolivar right here was shipped direct to Pittsburgh because the steel mills loved it. This is a sedimentary rock formed by the skeletons of plants and animals in the ocean. Millions of years and billions and billions and billions of little tiny microscopic one-celled animals and plants, they formed a little shell or a little skeleton around their body, around their one cell, just a little like bubble around them. And when these things they died, they'd settle to the bottom of the ocean and build up this stuff. And it took millions of years to accumulate this. And then the heat and pressure, this was kind of fluffy when it settled to the bottom, but buried, down under miles maybe of other rock, it got pressed into a solid rock. So this is actually a kind of limestone. I've labeled it Dolomite, but it's actually a kind of limestone. So that's the limey skeletons from these plants and animals that settle to the bottom. And this is the same thing, you hear about the chalk cliffs of Dover. That's exactly the same thing. That's another kind of limestone, only in that case, they were a little fluffier, didn't get compressed quite as much, so the rock is softer than this kind of rock. And that's just a matter of how much it was squashed and compressed after they were buried.
It's
pretty heavy. Pretty heavy. It's good. Yep. And then, okay, so that's one kind of sedimentary rock. Here's another one. This is sandstone. I'll pass this around. I collected this out. This was out around Hancock. And this sandstone was basically just what you imagine. This is sand grains. So this usually happened deep in the ocean, where you had these little, these oceanic things floating around the deposit. This is basically a shoreline thing, or from streams or rivers, where sand grains were deposited, or an ancient beach. And sand grains are deposited. And if that place stayed a beach for millions of years, then you could build up a lot of sand. And again, under the weight of the overlying sand, after a while it was hardened into a rock. And this is from a formation. In addition to the labeling the time, different layers of rock were given different formation names, they were called, and they were named because that way they were recognizable, and they could say, okay, I see the same kind of rock over here, so they name it like a formation. It was a way of identifying. So this was called the Oriskany Sandstone. This is a really famous sandstone. This was formed when the whole eastern half of the United States was under the ocean, and it was basically a beach. And there's this huge, thick deposit of this sandstone. And the interesting thing about this one is it's loaded with fossils of extinct kind of clamshells. These are brachiopods. So this was from a beach, and it still has the remains, you'll see in it, of the trapped shells. And as a matter of fact, this out around Hancock, out around in that same area, there's a company that that mines this stuff, and a lot of the silica that we buy, we use silica as a raw material on the glazes, comes from this formation. Because, as you notice, it's fairly clean, it's fairly light-colored. Silica by itself is mostly white, so it's fairly clean. It's got a little bit of iron in it, but it's clean enough, and they can just they dig it up, crush the rock, and run it through a screen and sell it. It's fairly pure silica. And it's mostly, that's an ancient beach, basically, that was buried. And then the last one I have here, this is shale, and to me, this is the most interesting one. This is clay. This is natural clay that was deposited and again compressed by lots of layers of clay, and it was pressed into a rock. But the interesting thing, this is from Martinsburg, West Virginia. There's the whole middle of the valley south from Martinsburg. There's this big belt of clay that exists. And the interesting thing, if you smell this, it smells like clay. I mean, so it's still actually. This is still, I'm going to say, 400 million years old. But it still smells like clay. It's amazing. Smell it? Isn't that amazing? Yeah. Yeah. So that's just clay that got buried and compressed hard enough it's still a very soft rock, but it got compressed enough to make it solid into a rock. And it's just the weight. Yeah. Yeah, iron. Yeah. Yeah. So those are sedimentary rocks. And lastly, there are metamorphic rocks. And these are the rocks these are pre-existing rocks that got changed. So it could be igneous rocks that got changed into something else, or sedimentary rocks that got changed into something else, or metamorphic rocks that got changed again into something else. Okay? And a good example of that, this is an example of a metamorphic. We're going to talk about this with the local history, but this originally started out looking kind of like the shale. Only it got squeezed by heat and pressure. And if you notice also, if you look at it on the end, it got bent. The rocks actually got bent. And this, so as part of from the pressure, so if you press on that enough and you squeeze it and you compress it and squish it around, you get, this is called phyllite. It's a kind of metamorphic rock. But you can see where it actually got bent. So at this point, the rock was actually kind of like toothpaste, and it got squished. Okay. Just a couple of quick definitions before as I should have mentioned long before. Basically, a mineral, the word mineral is basically just a naturally occurring compound, and it's basically an inorganic compound. In other words, it's not related to life. It's not a carbon compound. So it's a naturally occurring inorganic compound, which just means it's not life related. It wasn't living, it's not life related. And a rock is basically an assemblage of minerals. You can have a rock that's only made up of one mineral, but in the general way, you think about the rock as an assemblage or a collection of minerals.
The Potter's Roundtable is brought to you by Washington Street Studios and our patrons. If you enjoy the show, please subscribe, give us a 5-star review, and tell your friends. If you want to learn more about Washington Street Studios and shared studio memberships, please visit our website at www.hfclay.com. Thank you, and we'll see you again next time on the Potter's Roundtable.